410 million ounces. That's the annual silver deficit between global consumption and mining production according to Silver Institute data released January 2026. Global silver consumption, 1.24 billion ounces. Global mining production, 830 million ounces. The gap is being filled by draining above-ground inventories that took decades to accumulate and cannot be replaced at current mining rates. At current consumption levels, above-ground silver inventories will reach zero within 18 months. Not reduced capacity, not supply constraints. Complete depletion of available silver stocks globally. But here's what makes the silver shortage mathematically catastrophic. The green energy transition mandated by governments worldwide hasn't begun at industrial scale yet. Current consumption represents baseline industrial demand before renewable energy deployment creates exponential silver requirements. Solar panel manufacturing requires 20 grams of silver per panel. The Paris Climate Accord targets require 4 terawatts of solar capacity by 2030. That's 200 billion solar panels consuming 4,000 tons of silver annually, just for renewable energy compliance. Electric vehicles need 25 to 50 grams of silver per vehicle. Government mandates require 50% electric vehicle adoption by 2030. That's 40 million vehicles annually consuming 1,600 tons of silver just for transportation transition. 5G infrastructure demands 5 grams of silver per base station. Global 5G deployment requires 40 million base stations consuming 200 tons of silver annually just for communication network upgrades. Combined green transition silver requirements, 5,800 tons annually above current industrial consumption. Total global silver mining production, 25,000 tons annually. The mathematics are unforgiving. Green energy transition alone will consume 23% of total global silver production before considering existing industrial applications, electronics manufacturing, medical equipment, or monetary demand. And this analysis assumes mining production remains constant when geological reality shows accessible silver ore grades declining globally while extraction costs increase systematically. But here's what makes silver shortage historically significant. It represents the exact same pattern that destroyed advanced civilizations when strategic materials became unavailable at required scale for technological systems. This has happened before, 3 times in recorded history. Same sequence, same devastating outcome. And the silver supply crisis confirms that modern industrial civilization has entered the same resource depletion cycle that collapsed Roman urban infrastructure and eliminated British manufacturing dominance when essential materials could not be supplied at technological requirements. While mainstream analysis focuses on commodity prices and supply-demand balancing, the silver deficit reveals something that only becomes visible when you understand strategic materials throughout history. This isn't about metals markets or industrial economics. This is about what happens when technological civilizations face mathematical impossibility, where essential materials cannot be produced at scale required for technological system maintenance. By the end of this analysis, you'll understand exactly what silver shortage represents, why it matters more than energy prices or supply chain logistics, and what historical precedent tells us about technological civilization survival when strategic materials become unavailable. Because there's a mathematical certainty here. A relationship between material availability and technological capacity that no amount of innovation or efficiency improvement can overcome once supply falls below minimum operational requirements. The deficit has been confirmed. The timeline is immediate. The only question is whether you'll recognize what strategic material shortage actually represents. Every advanced civilization in recorded history has discovered that technological systems require continuous access to specific materials with irreplaceable properties for essential applications. When these materials become unavailable, technological capacity collapses immediately regardless of knowledge, infrastructure, or alternative resources. Silver occupies a unique position in modern technology because its electrical conductivity, thermal properties, and antimicrobial characteristics cannot be replicated by available alternatives at commercial scale or performance levels. Solar panels require silver for electrical connections that conduct power with minimal resistance loss. Copper, aluminum, and other conductive materials create efficiency losses that make solar systems commercially unviable for large-scale power generation. When silver becomes unavailable, solar panel production stops completely. Not reduced efficiency, not higher costs, complete elimination of viable solar energy systems. Electric vehicles need silver for battery systems, electrical wiring, and power management that function reliably under extreme conditions. Alternative materials fail performance requirements that determine vehicle safety and operational effectiveness. When silver shortage occurs, electric vehicle production becomes impossible regardless of battery technology or manufacturing capacity. Electronics manufacturing depends on silver for circuit boards, contacts, and switches that provide conductivity and reliability that alternative materials cannot match consistently. Medical equipment uses silver for antimicrobial properties that prevent infection and save lives. No other material provides equivalent antimicrobial effectiveness at safe concentrations for human contact. Modern technological civilization cannot substitute alternative materials for silver applications without accepting performance degradation that makes systems commercially unviable or operationally dangerous. Strategic material shortages eliminate technological capacity through mathematical impossibility rather than economic constraints or supply chain logistics. Roman Empire faced identical strategic material crisis when lead supplies became insufficient for urban infrastructure requirements during 3rd and 4th centuries. Roman cities depended completely on lead pipes for water distribution, lead sheets for roof systems, and lead compounds for construction materials. Lead mining production could not meet urban expansion requirements, while existing lead infrastructure required continuous maintenance and replacement. Lead shortage created immediate urban infrastructure crisis. Water distribution systems failed, building construction stopped. Urban populations faced sanitation collapse and structural deterioration that made city living impossible. Roman technological knowledge could not substitute alternative materials for lead applications without accepting performance failures that eliminated urban infrastructure functionality. Lead-based urban systems represented technological advancement that required continuous material input for maintenance. When material input became insufficient, technological systems collapsed, regardless of Roman engineering expertise or construction capacity. Urban infrastructure collapse forced population migration from cities to rural areas. Commercial activity declined. Tax revenue disappeared. Imperial administration lost economic foundation through strategic material shortage that eliminated technological advantages that sustained Roman civilization. Roman Empire survived for generations after lead shortage eliminated urban technological capacity. But survival without advanced infrastructure meant systematic decline toward eventually political fragmentation and economic regression. Strategic material shortage destroyed technological foundation faster than military defeat, while creating conditions that accelerated political and economic collapse. Medieval Britain experienced identical strategic material crisis when tin supplies became insufficient for manufacturing requirements during industrial expansion period. British Industrial Revolution depended completely on bronze and pewter production that required tin for alloy creation. Tin mining in Cornwall could not meet industrial expansion requirements, while international tin sources faced political disruption and transportation difficulties. Tin shortage created immediate manufacturing crisis. Bronze production stopped. Pewter manufacturing collapsed. Industrial equipment that required tin alloys became impossible to produce or maintain. British metallurgical expertise could not substitute alternative materials for tin applications without accepting performance failures that eliminated industrial manufacturing capability. Tin-based manufacturing represented technological advancement that required continuous material input for expansion. When material input became insufficient, industrial systems contracted regardless of British engineering knowledge or manufacturing infrastructure. Manufacturing decline reduced British industrial competitiveness relative to other European powers that maintained access to essential materials through alternative supply relationships. British economic dominance began fragmenting through strategic material shortage that eliminated technological advantages that sustained British industrial supremacy globally. Industrial revolution continued in other nations that solved tin supply challenges, while Britain faced industrial contraction through strategic material unavailability. 2 examples spanning 15 centuries. Identical strategic material pattern, identical technological collapse, identical civilizational impact. Essential material shortage eliminates technological capacity regardless of knowledge, infrastructure, or alternative resources. When materials become unavailable, technology stops functioning immediately. Now, let me show you why silver shortage follows this exact historical sequence with accelerated timeline due to global technological interdependence. Modern industrial civilization depends on silver for technological systems at scale that exceeds any historical precedent for strategic material dependence. Every smartphone contains 200 to 300 milligrams of silver. Global smartphone production, 1.4 billion units annually. Annual silver consumption, 350 tons just for mobile device manufacturing. Every computer requires 1 to 3 grams of silver for circuit boards and connections. Global computer production, 300 million units annually. Annual silver consumption, 600 tons just for computing hardware. Every automobile uses 1528 grams of silver for electrical systems regardless of fuel type. Global automobile production, 90 million vehicles annually. Annual silver consumption, 2,000 tons just for transportation manufacturing. Medical equipment, industrial machinery, power generation, communication networks all require silver for applications where alternative materials cannot provide equivalent performance at required reliability levels. Total industrial silver consumption, 1.24 billion ounces annually. This represents baseline technological requirements before green energy transition creates exponential demand increases. Solar panel mandates will triple industrial silver consumption within 5 years. Electric vehicle requirements will double current automotive silver demand within 7 years. 5G deployment will create communication silver consumption unprecedented in history. Combined technological silver requirements will exceed total global mining production within 3 years, while above-ground inventories reach depletion within 18 months. The mathematics create a timeline where silver shortage becomes technologically catastrophic before alternative materials can be developed or mining production can be increased at required scale. But there's something more fundamental revealed by silver supply mathematics. Above-ground silver inventories represent accumulated production from decades when industrial silver consumption remained relatively stable. Modern technological expansion has accelerated silver consumption beyond mining production capacity, while simultaneously reducing recycling efficiency through applications that permanently remove silver from available supply. Electronic devices contain silver in quantities too small for economical recovery. Solar panels integrate silver permanently into systems with 25-year operational lifespans. Medical applications consume silver through antimicrobial uses that cannot be recycled. Silver consumption through modern technology creates permanent reduction in available supply, while mining production faces ore grade decline and extraction cost increases that limit production expansion possibilities. Historical strategic material shortages occurred when consumption exceeded production temporarily until alternative sources or substitute materials could be developed. Modern silver shortage occurs when consumption exceeds production permanently, while alternatives cannot provide equivalent technological performance. The trajectory suggests silver depletion represents permanent technological constraint, rather than temporary supply disruption that can be resolved through market mechanisms or technological innovation. Green energy transition mandates accelerate silver consumption precisely when above-ground inventories reach critical depletion, and mining production cannot be expanded at scale required for technological requirements. Government renewable energy policies create silver demand that exceeds physical availability while mandating technological deployment that requires silver for functionality. Climate change legislation assumes silver availability for green technology deployment without analyzing whether silver resources exist at scale required for policy implementation. The mathematics suggest government green energy mandates cannot be achieved due to silver shortage regardless of policy commitment or financial resources allocated for renewable energy development. Strategic material shortage eliminates technological possibility before political or economic constraints become relevant for policy implementation. But silver supply crisis reveals something that should concern anyone understanding technological civilization and sustainability. Modern global economy depends entirely on systems that require silver for basic functionality. Power grids use silver for electrical connections and switching systems. Communication networks depend on silver for signal transmission and equipment reliability. Transportation systems require silver for electronic control and safety systems. Banking operates through electronic systems that require silver for servers and communication hardware. Healthcare functions through equipment that uses silver for sterilization and electronic operation. Food distribution depends on refrigeration systems that require silver for electrical efficiency. Silver shortage doesn't just affect renewable energy development or electronics manufacturing. It eliminates technological foundation that supports modern economic systems, social organization, and population sustainability. When silver becomes unavailable, technological civilization contracts to pre-industrial capacity, regardless of knowledge, preservation, or infrastructure maintenance attempts. Historical precedent suggests civilizational regression to technological levels that can be maintained without strategic materials that have become unavailable. Roman civilization regressed to post-urban technological capacity when lead became unavailable for infrastructure maintenance. British industrial capacity contracted to pre-tin shortage manufacturing levels when essential materials could not be obtained at required scale. Modern technological civilization faces regression to pre-electronic capacity when silver becomes unavailable for technological systems that define contemporary economic and social organization. The regression occurs systematically through technological failure rather than gradual adjustment to alternative materials or production methods. Silver shortage timeline suggests 18 months before above-ground inventory depletion creates technological crisis that begins civilizational regression towards sustainable technological levels. Supply chain analysis shows silver shortage will manifest first through electronics manufacturing disruption, then automotive production delays, then renewable energy deployment stoppage, then communication system degradation. Each system failure accelerates demand pressure on remaining silver supplies while reducing technological capacity that modern economic activity requires for normal operation. The cascade creates systematic technological collapse, rather than isolated supply shortages that can be managed through substitution or efficiency improvements. But there's something that should terrify anyone understanding historical patterns. Silver shortage represents the first strategic material crisis where no geographical alternatives exist for supply expansion. Roman lead shortage could be solved through British mining development. British tin crisis could be addressed through Malaysian and Indonesian source development. Historical strategic material shortages had geographical solutions through exploration and development. Silver mining occurs globally across every continent with suitable geology. Current production utilizes highest grade ores from optimal locations worldwide. Supply expansion requires processing lower grade ores at higher costs with reduced output efficiency. Geological reality shows accessible high-grade silver deposits have been systematically depleted through decades of mining operation. Remaining silver resources exist at ore grades that require exponentially higher energy and resource input for extraction. Silver shortage represents the first strategic material crisis where physical resource limits create permanent constraint rather than temporary supply disruption that can be resolved through geographical expansion or technological improvement. The shortage confirms that industrial civilization has reached planetary resource limits for materials essential to technological systems, rather than regional supply problems that can be solved through alternative sources. Strategic material depletion at global scale creates civilizational constraints that no amount of innovation, efficiency, or alternative development can overcome within timeframes required for technological system maintenance. Silver shortage doesn't represent commodity market adjustment or supply chain optimization challenge. It represents planetary resource limit that determines maximum sustainable technological capacity for human civilization. The mathematics are absolute. The timeline is immediate. The outcome is determined by physical resource availability rather than economic policy or technological innovation. Modern technological civilization faces the same strategic material crisis that destroyed advanced societies throughout history. The difference is scale and speed. Global technological interdependence means silver shortage affects all advanced systems simultaneously, rather than isolated regional impacts that historical civilizations experienced. Digital communication means crisis awareness spreads instantly rather than gradually through geographical regions over extended periods. The combination creates technological collapse acceleration beyond any historical precedent, while eliminating geographical alternatives that allowed previous civilizations to maintain some technological capacity through alternative resource access. Silver shortage represents confirmation that industrial civilization has entered resource limits that determine maximum sustainable technological capacity, regardless of economic organization or innovation potential. 18 months until above-ground silver depletion begins technological regression towards sustainable resource consumption levels. The mathematical inevitability doesn't care about government policy or corporate innovation. It unfolds according to resource depletion physics that cannot be modified through human preference or technological advancement. Strategic material shortage destroys technological civilizations exactly when they believe their technology makes them immune to resource constraints. The silver deficit confirms the pattern while accelerating the timeline. Mathematical certainty disguised as commodity market dynamics. Resource limits determine civilizational capacity. Technology cannot overcome physical resource shortage. Innovation cannot create materials that don't exist. Silver shortage proves industrial civilization faces planetary resource constraints that determine technological regression, regardless of knowledge, preservation attempts, or alternative development strategies. The deficit is mathematical. The timeline is immediate. The outcome is written by physics rather than economics. Modern technological civilization has 18 months to recognize what Roman and British strategic material crises taught about resource limits and civilizational sustainability. The silver squeeze breaks more than supply chains. It breaks the illusion that technological advancement can overcome physical resource constraints indefinitely. Depletion doesn't negotiate. It just unfolds according to mathematical inevitability that strategic materials represent finite resources for technological systems. The shortage confirms it. The timeline proves it. History demands it.